Our world today relies on underwater infrastructure. Underwater pipelines, cables, and structures power today's society. These objects require regular inspection and maintenance. But this is often very hard to do. Right now, we are relying on human divers, which takes a long time, is costly, and often dangerous. Underwater robotics has made rapid development in recent years and offers very promising solution to underwater maintenance and inspection. Existing sensing solutions that are used on land often don't perform very well underwater. Stereo cameras can't match on underwater scenes because they often lack features and the water is very murky, blocking light. LiDARs, or standard time-of-flight cameras, don't work at all because they use infrared light, which water blocks completely. So people often resort to sonars, but these sensors are very expensive and perform poorly at close ranges, which is often the desired mode of operation for infrastructure inspection. Our project aims to fill this gap in sensing technology. We're making a custom time-of-flight camera that is able to take 3D images of underwater environments at close ranges. A time-of-flight camera works by illuminating the scene and measuring how long it takes light to bounce back into every pixel of the camera. Our camera is different from what you can buy commercially right now because we use visible light instead of infrared light. By illuminating the scene with visible light, we're able to use our camera underwater, providing a crucial tool for underwater robotics and infrastructure inspection.
Our overall architecture consists of two modules. One on the left is our illumination module, which lights up the scene. One on the right is our imaging module, complete with depth camera chip and optics. These are all contained within waterproof enclosures.
So how does a time-of-flight camera actually work? Our illumination module modulates light at 24 MHz and illuminates the scene. Then the objects in the scene reflect this modulated light back into the camera module. The camera module is able to compare the phase of the received modulation with the phase of the transmitted modulation wave. This phase difference is directly proportional to distance to every point in the scene. By calculating this phase difference for every pixel, the camera is able to reconstruct the scene in 3D and produce an accurate depth map of the entire scene.
Within our imaging module, we have this custom PCB, which has a microcontroller communicating over a high-speed interface with our camera chip and sends depth images to the outside world over Ethernet.
Our illumination module consists of two circuit boards. The current supply circuit boards on the top right provides high current that is required for bright LED illumination. And our LED modulation boards contains the LEDs themselves, as well as a sophisticated modulation circuit that enables us to modulate the light at 24 MHz to enable accurate depth perception. Modulating a lot of current at high frequency is a complex electrical engineering challenge. We started with computer simulation to validate our circuit before we went with manufacturing a physical board. Then we did very careful layout, component selection, and placement to make sure that our circuit behaves as expected at these very high frequencies. Finally, thermal design was a very big concern. LEDs are very powerful and emit a lot of heat, and so this heat needs to be dissipated into the outside world. So we went ahead with an aluminum core printed circuit boards for LED modulation, as well as a custom machined aluminum backplate.
Connecting up all of our systems is a very hard software and firmware challenge to solve. We have an image sensor that's outputting data at a very high frequency, as well as an Ethernet interface to transfer all of that data to. In order to accomplish this, we had to change around configurations of both our microcontroller as well as the sensors to make everything work at an expected 10 FPS rate. In addition, we had to generate clocks that matched precisely between both the LED modulation as well as the image sensor to ensure that we could have accurate enough depth estimation. And here you can see some validation of these signals. Finally, we had to write a Python program to actually visualize these depth maps, get packets from Ethernet, and show us what the underwater aquatic environment actually looked like.
This video shows our overall testing setup. You can see that both of our modules are waterproofed and also placed pretty deep in an aquatic tank. You can see the LED modulation actually occurring here. And so what we're actually looking at is when it turns off, the camera is not actually collecting a frame, but when the LED is on, it is modulating at a very high frequency. And you can also see an example of one of the objects that we put in front of it. This first still image shows a camera calibration board that we put into the water to try and get depth images off of. In this visualization, we see a few key pieces of information. In the top left is an image of phase of the light coming back to the image sensor over time, which is proportional to distance. Below that, you see a filtered version of this same image. In the top right, you actually see the amplitude of the light being received, which is more indicative of color and the actual form of the image. On the bottom right, you see a histogram of depth over time, which you can see change as we move this camera calibration board up and down. This setup shows us lowering a fairly thin pipe into the water, which we use to accurately determine the resolution of the sensor and whether it could see thin/small objects. And finally, this last setup shows multiple different objects in the tank. We can see 2 different camera calibration ports as well as a pipe. And notice that they're all at different translations or depths within that tank. And you can see that the depth values are actually fairly different between the different objects as we move them around, showing that our camera is actually able to discern depth meaningfully.